Okay, now we're going to find some things that describe the behavior of graphs, namely where finding intervals where functions increase, decrease, or remain constant, perhaps. We're also going to find things called maxima, local maxima and local minima, and absolute maxima and absolute minima. And this will generally, for the most part, describe the behavior of the graph in terms of where it's rising, where it's falling, where it's at a dip or a low point, or a peak or a high point. Okay, so before we talk about intervals of increase and decrease, before we talk about maxima and minima, if you look in the first box, it says a function f is an increasing function in an open interval if f of b is greater than f of a for every two input values a and b where b is greater than a. So f of b is greater than f of a whenever b is greater than a. Okay? What that means graphically is if we just draw a small xy plane real quick and we label the x-axis with two values a and b. So again, this is where b is greater than a. To say that a function is increasing is whatever point that corresponds to a, it always must be the case that if b is to the right of a, the output at b will be higher than the output at a. Okay? So on the horizontal here, the height of the point corresponding to a would be f of a. The height of the point corresponding to b would be f of b. And again, we're just saying that if you're moving to the right on the graph, the y-coordinates get larger. In this case, we do have f of b larger than f of a. Okay? All right, so what about decreasing? A function's decreasing in an interval if f of b is less than f of a, so the y-coordinate at b is less than the y-coordinate at a, if for every two input values a and b, b is greater than a. So again, here's my set of coordinate axes, x-axis, y-axis. I have two inputs a and b where b is larger. This time what must be true is that whatever height the point is at a, which is denoted by f of a, as if we're going to move to the right or increase our input, for a function to be decreasing, our inputs must get smaller or decrease. Okay, so again, we have here that b is greater than a, but f of b is less than f of a. Okay. So it's the saying, as we move to the right on the graph, if we're decreasing, the graph is going down. Now, the third definition here, it says f has a local maximum that should be bold or highlighted at a point b in an open interval. Okay, so we're not looking at an entire domain, just a piece of the domain from some number a to some number c. If f of b is greater than or equal to all the other f of x's in that interval, f of b is what's called a local maximum. So again, for instance, I might have a graph. Here's a, here's c, and maybe the graph does something like this on that interval. It starts going up and then comes back down. Okay. So on that interval, or just that piece of the graph, now again, the graph could have more pieces, right? It could move somewhere to the left and it could come up to the right. But if we just look at one piece of the graph, then on that interval, whatever the highest point is, okay, if that occurs at b and the height of that point is f of b, then f of b is a local minimum or maximum, Sometimes I just write local max. So y coordinates are the local maxes. F of b is just saying b is the input that gives rise to that local max. Okay. Now again, we don't care if it's the highest point on the whole graph, because again, maybe the graph continues and eventually rises again. But on this interval, b corresponds to the highest point, which has a height of f of b. That's the local max. Now, last sentence, it says f has a local minimum at b in some interval from a to c if f of b is less than or equal to all the other function values. on that interval. So again, for a local minimum, there we have a vertical and horizontal axis, or x and y axis. We have an interval from A to C. And this time maybe what my function does is it dips down and comes back up. Okay, actually let me maybe emphasize this a little differently. There we go. Okay, so again, the function might do all sorts of other stuff. It might come back down and go to the right. On the left side, it might do some crazy stuff. But if we just restrict the graph locally to one piece of it, then there's got to be a lowest point, and that's at a value of b, and then its y-coordinate f of b in this case is a local minimum value. Okay, and together the local mins and local maxes are what are called local extrema when they exist. Okay. Now, one thing I want you to notice is that a local max or min can never happen at an end point. That's why I have the open circles on the end. It's not the entire graph. Those aren't necessarily endpoints. But if there's a place where the graph goes down and comes back up, you have a local minimum. If there's a place where the function goes up and comes back down, so it increases and decreases, you're at a local maximum. Okay, so let's do a couple examples. There's also the definition of an absolute max and min. And maybe I won't draw a picture for this, but an absolute maximum is just a y-coordinate of a highest point on the graph, if there is one. An absolute minimum is the y-coordinate of the lowest point on a graph. Okay, so example 5. With technology, let's use the graph of this function. So we're going to use something like Desmos to find the intervals in the domain, which is all real numbers, to find out where the intervals in the domain on which f of x is increasing and f of x is decreasing. And we're going to also find any local maximum and minimum values if they exist. So let's take a little detour here and go plot this function in Desmos. Okay, so hopefully I didn't already say it, but an absolute maximum is it's a point f, or it's a function value f of c that's greater than or equal to all the other outputs where x is in the domain. So literally the absolute maximum is just the y-coordinate of any highest point on the graph. And similarly, the absolute minimum is the lowest point of, or the y-coordinate of any lowest point on the graph. So we're going to go ahead and use technology, or with technology, we're going to use the graph of this function, f of x equals x to the fourth minus 2x cubed minus 4x squared plus 2x plus 3. We're going to find the intervals in the domain in which the function is increasing or the graph is rising, and the intervals for which the graph of f of x is decreasing or the graph is going down. We're also going to find any local maximum and minimum values if they exist. So let's take a little detour here to Desmos. Okay, so here we are. I am in Desmos. And I have just typed in the function in the space it provided me. I'll kind of show you what I did. I just typed f of x, and then I did equals x, and then you can hit shift 6 to get a power, like to the fourth. You hit the right arrow to go down, subtracting 2x, again shift 6 to get powers. So I'm just using shift 6 to get powers, and then I'm using the left or right arrow to move around the expression. But there's our function, and I want to find the intervals on which the function increases or decreases, and I also want to find any maximums or minimums if they exist. Now, first thing that I think is important is resizing the window. So what you'll notice is, and this is because the function has a highest power of 4, which is even. We'll talk about this later. This is called end behavior. But you'll notice the graph rises up on both ends, right? If you go left, the graph goes up. The farther you move to the right, eventually the graph is going to also rise. So resizing this is really important. Now, when I zoom out, I'll see that the lowest point on the graph has a y-coordinate of negative 10, but there is no highest point because the graph is constantly rising. Now, the graph crosses the x-axis at the point negative 1, 0 for the first time, and it does it for the last time at 3, 0. So in the top right, I'm going to click on this little wrench that you guys are going to see a little graph settings display pop up. And I'm going to restrict the function's x-axis to go from -5 to +5. Okay? And I'm going to change the y-axis from about -12, maybe 15, and maybe I'll go to +15. Okay, so here's a much better sized graph, and I can even slide a little bit to the left. There we go. Okay. So here's a graph of this function. Now, what I'm going to do is, the nice thing about Desmos is you can highlight certain points. Namely, you're going to see there's all these places. I mean, I guess it's giving you each point where it crosses the x-axis. But I'm going to click on the points where it turns from decreasing to increasing, where it turns from increasing back to decreasing. And then there's a third point where it goes from, again, rising or falling to rising. So I can find those 3 special points, and then I'm going to use various colors here. Let's go ahead and anywhere the function is going down, I'm going to highlight in purple. Okay. Anywhere the function is rising, I'm going to leave that in green. Okay. So in the left, in the little space that I have provided here, I know that the function f... Oh, before I even do that, I'm going to draw a corresponding picture on the x-axis. For the parts where the function is going down, I'm also going to highlight the graph in purple. Okay. There we go. So there's a picture on the x-axis of the values of x where the function would be decreasing. The function is said to be increasing everywhere else. Okay, so on the left, what I'm going to say then is f is decreasing, and I'm looking for intervals in the domain. So anywhere on the x-axis where the function is going down, first of all, this happens on the interval from -infinity. You'll see that at the point -1, 0, it stops decreasing and changes to increasing. So it's decreasing from -infinity to -1, and it begins decreasing again at an x-coordinate of 0.219, and it stops decreasing at the x-coordinate of 2.281. Okay. F is increasing everywhere else, which would be from, those are the parts of the graph that I left in green. So you'll see that the function goes up from the x-coordinate of -1 to the x-coordinate of 0.219. And again, it starts going up from 2.281, but after that it goes up forever. So we say the interval it's increasing on is 2.281 to infinity. Okay. Now, I can also talk about any local maxes or mins. Now, essentially, anywhere the function changes from decreasing to increasing, that's essentially where you're going to have a local minimum. So what do we see? At the point -1, 0, okay, or in other words, when f is -1, when x is -1, f of -1 is 0. Okay, you have a low point. So I'm looking at this point right here. So we have a local min of f of -1 equals 0. And there's another one on the right side of the graph. There's another place where the function goes from falling to rising, and that happens at 2.281. And the output there is the local min of -9.915. And there's just one local max. That's that point where it changes from increasing to decreasing at 0.219. So there's a local max of f of 0.219, which is that y-coordinate of 3.227. Okay, so I've now found the intervals that the function's increasing on, the intervals the function is decreasing on, and we found some local max and mins. You can think of them as either peaks or valleys or places where the function changes from rising to falling or falling to rising. Okay, let's do one more example before we call it a day. Okay, example 6. Now, using the function from example 5, let's suppose that the domain of that function was just restricted to the x values of -2 to +4, including -2 and 4. I still want to find the intervals in the domain on which f of x is increasing and where f of x is decreasing. We're going to find any local and absolute extrema. So we mean local max and mins and absolute max and mins. Okay, so note extrema is just a term that means both maximum and minimum values. So local max and mins and absolute max and mins. Let's go to Desmos again. Okay, so here we are. We got our Desmos graph and calculator. Now, I've already entered in the command. If you look at my second entry here, I've just typed in the same function, but in curly braces, I've typed in, let's see if I have the right. Let's instead go from -2 to 3. Okay, so my apologies. I know that in the handout, I probably said -2 to 4, but instead let's do -2 to +3. Okay. All right. So back to Desmos. Now that we've made that change. Okay, so we're just going to look at the function on the interval from -2 to 3. Now, of course, here's the entire function. And then I can click on the little number 1. I can click on the green squiggly line on the left, and that'll just give me only the second function that we're graphing. Okay, so again, I could play with my window. If something's not fitting, a lot of times you have to zoom out to see how wide your x-axis should be and how tall your y-axis should be. But I think I'm good just working with what I have here. Okay, so now, just like before, we're going from -2 to 3. I'm going to highlight the graph in purple where it's decreasing. As a matter of fact, though, there's a couple points that I should click first on the graph. I should click those peaks and valleys to get the coordinates of where the function changes from falling to rising and rising to falling. Okay, so I'm going to highlight the parts of the graph where the function is decreasing in purple. Okay, and on the corresponding x-axis, I can highlight the parts of the x-axis where the function is going down. Okay, so this time when I say where f is decreasing, it's going to decrease on those intervals from -2 to -1. Okay, so right, our domain starts at -2, and the graph falls until I get to -1, and it starts falling at 0.219 until we get to the x-coordinate of 2.281. Okay, so I'm using the x-coordinates of the 2 points where the graph starts falling and where it ends falling. So it starts falling at 0.219, it ends falling at 2.281. F is increasing on the interval from, okay, on the graph, it starts increasing at -1 and stops again at 0.219. And it starts increasing again at 2.281. And you'll see that on the graph, it stops increasing. Our domain ends at positive 3. Okay. All right. And then, same as before, F has local mins. There's 2 of them of f of negative 1 equals 0 and f of 2.281 equals negative 9.915. F has a local max still of f of 0.219, which is 3.227. And let's see. The absolute maximum would be the value of the function at negative 2. Okay, that would be our highest point. Our lowest point is still also one of the local minimums. Okay, so I'll write this on the next page. We have a highest point and a lowest point. Okay, and the highest point is at a height about, I don't know, it's pretty close to 15, approximately 15. Okay. And the lowest point, we have the y-coordinate of negative 9.915. So, f of negative 2 equals, which is approximately 15, is an absolute max. Okay, because that is the highest point that's the value corresponding to the highest point on the graph. And f of 2.281, which is 9.915, is the absolute minimum. Okay, so you'll notice that local max and mins can't occur at the endpoints of a graph, but absolute maximums can. Okay. All right, well, that concludes the video. That's at least an introduction to this section on rates of change and behavior of graphs. Again, thanks for tuning in. Until next time, take care, and we will talk to you soon. Thank you. Have a good one.